Right, so good pre-noon, just between you and lunch. And I am going to be talking us through, and I'd actually like to thank the previous speaker for that little sort of journey into history, because I think it's really exciting to be working in this industry at a time where, thanks to many of the companies that you'll see in the booths here, that hardware is making phenomenal leaps, whether it be in qubit count, whether it be in dealing with error, and that is something in many ways that reflects what happened in the history of classical computing. Now, Classiq is, and obviously you have questions to the QR code. I'll leave it up for a second. So Classiq, as you may be able to guess from the name, and there are many people who wonder how it's pronounced, but on the record, it's Classiq. Takes a lot of inspiration from what happened in classical computing. And whether it's with sort of traditional PCs or DSP or FPGA, these are in a very symbiotic relationship. And as quickly as the hardware progresses, you're not going to be able to get the most out of it if the software isn't able to extract the very maximum of what that hardware can achieve. And that's very much what underpins what Classiq is all about. Making sure that the software is ready for whatever hardware happens to be able to offer at any given time, and squeeze that little bit extra out of it, perhaps. So we're quite fortunate in the sense that we get to engage with a broad range of the quantum industry, whether it's students, whether it's enterprise customers, whether it's our cloud partners, and our hardware partners behind them. And that allows us to have quite a privileged position and see perhaps what's happening, both in terms of the people, in terms of the types of applications that are being explored, and also, of course, perhaps under the hood of a lot of the software, all of which is going to be absolutely crucial to allowing utility in this utility area, as we hear it, and coined by IBM, in order to really make the most of this sort of intermediate period. So what Classiq is doing is built on these three pillars. Essentially, there's an operating system approach that we have, a compiler, or we'd say a true compiler. It's not transpilation as one typically knows it. And then an IDE environment, which is one of the new introductions that we've had since Q2B last year, which is really intended to open and democratize access to quantum computing in a way that will allow people who perhaps don't even have the depth of experience that has been needed so far in order to become proficient and active and successful in deploying algorithms across a whole range of different backends. So this is partly showing off what we've been doing over the last year, but it's also to sort of give some strength to that narrative. We kicked off the year with lots of commercial types of activities, whether that's collaborations with KPMG or NVIDIA and Rolls-Royce, really working on the application side, giving us a chance to understand how people want to code, the kinds of questions that they have. This has led to us opening a couple of offices to follow up on those commercial engagements. So if you happen to be in Boston or indeed in Tokyo, we'd be very happy to meet you there. But some of the other announcements we've had during the year touch more perhaps on things that relate to this journey to utility. One is that we've got some developments around benchmarking, and this is one of the things that we see a lot of customers interested in. What they want to test is different machines for different applications, and that's not at all an easy task if the software isn't designed to enable that. We've got a Quantum for Healthcare and Life Sciences center that we're establishing, so anybody who wishes to send questions about that later, please do. Part of bringing in utility, of course, is expanding the number of backends that people can have ready and easy access to. So yesterday we announced our work together with OQC on adding an additional backend for people to select from. And perhaps last, but maybe not least, is about how to get people coding and being more effective and really bringing down the barriers to application and industry vertical success, which is relevant for the students out there as well. and that's the GitHub repository that we launched yesterday, which I'd encourage you all to go and take a look at. But where does software fit in to this path to utility? And in that somewhat privileged software position of being in the middle, we get a lot of exposure to the quantum developers, from experienced all the way to novice. And we also, on the other hand, get a lot of exposure to the different backends and how they're progressing and what it is that our users, as the software provider, want to be exploring and want to be developing for. So if one looks at the developer end of things, it's been quite an interesting year from our perspective at Classiq, which is that there's something changing. Who is it that we want to bring with us on that development side into the quantum era? We see on the enterprise teams that we work with what used to be pretty much exclusively physicists turning into a slightly different cohort of people. We had one client in Japan who came to us and didn't have a large or trained up quantum team. They had an AI engineer and they had a machine learning engineer. And they said, well, what could we do with these guys? And within a space of 2 to 3 weeks, because of the ease of access, and I'll go into it in a bit more detail later, they were able to start deploying quantum algorithms in next to no time. And I think this is going to be something that we see becoming more and more important going forward. Who can we engage with? How many barriers can we bring down? How many applications can be built into the software? And I encourage you to go and look at the GitHub repository, and you'll see how much we're putting out there and making available. And I'll also touch a bit later on how we're doing that through the IDE interface as well. So on the one hand, yes, enterprise developers. We kicked off the year with a joint project with Microsoft targeting academic users as well, giving them free access to the software and also free computation. And that's been something that's been very, very interesting, very informative. We're now, I think, being used at more than 400 different universities from Arizona to Zimbabwe. And really, it's amazing to see how many places are exploring quantum. And one of the things we've been seeing there as well is the number of master's programs in quantum has essentially doubled. Quantum computing, that is, have doubled over the last year compared to the preceding year. Is the types of students are different as well. They're also not physicists. They're computational biologists. They're computational chemists. They're engineers, perhaps with a background in generative design. So these are people who have a computational background, but they don't have the quantum chops, perhaps, that you typically expect to see in these programs. And they're changing. The professors are changing how they teach. They change the kind of tools they need. And that steep learning curve needs to become shallower. So on the one hand, we're offering like GitHub in that context, where you'll find all kinds of tutorials. One of the things we promise is it will not break. So if there is a new version of the software, it will survive those kinds of things, so there won't be any unpleasant hiccups. Another thing that we're doing in terms of getting those developers up to speed and giving them a place to progress is we launched a Slack community this year, which everybody's invited to join. You don't even have to be a user. It's just a good place to meet like-minded people. And so this is the sort of work we're doing to be able to democratize coding for quantum computers, bring down the barriers, automate, make it more approachable. But of course, this rests on the underpinnings of what Classiq software is intended to do and how it works. And this is really the part where it relates to what I was hinting at earlier on of how does one approach making software for such a huge range of different types of hardware? How does one keep ahead of the number of qubits available or the noise that one has in various machines? And this is obviously a massive challenge for anybody who's coding. For those who are familiar with Classiq or even familiar with coding, will know exactly how big that challenge is. And every time there's an announcement about a larger machine with many more qubits, from Classiq's perspective, of course, we go, well, that's great, because this is going to be the moment where, in order to get the most out of those pieces of hardware, you're going to have to take a different approach. Because they're huge design challenges. Whether you're working at the level or thinking about sort of block level decisions, whether you're thinking about the resources that the hardware itself has to offer you, this is an enormously complex task, and obviously scales dramatically as, as the systems get more sophisticated, get harder. On top of that, these are very closely interrelated, and they depend one on the other. And so what Classiq is doing with our approach to, really a new approach to coding, is to change that dynamic. And again, the name of the company is Classiq, inspired to an extent by classical chip design. So the automation of design, we're talking about the transistors that we saw earlier on, and the trillions and trillions of them that may be in this room. Designing those chips is no humanly possible task, and it's an automated one, and there are companies who are dedicated to doing that. The same thing can be seen if you've ever looked at generative design in mechanical engineering, where people will look at something, they'll actually look, and it gets very difficult because you're restricted by what you can think of. And this is where one can really take, can understand the inspiration of what underpins our platform. I'll take a walk under the hood in a few moments, but really what we're offering is an end-to-end approach, lowering the barriers to entry to coding. So there's a platform that allows you to work at a much higher level, so you can design and debug and optimize and also execute all within the platform, but the interface is very, very high level. It doesn't require you to get down into the assembly language, into the gate level design that's necessary. There's a bit of a magic button where all of that laborious work is taken off of your hands, and it's prepared in a hardware-aware way for execution. This is the interface. We actually launched it earlier in the year. It's a SaaS sort of type of product, so it's browser-based. You can log on through any browser that you'd like to. And you'll see over on the left there the stages that I mentioned earlier: synthesis, modeling, circuit investigation, jobs where you can actually see, as you would with your printer or any other execution task, where you are in the line to get your results, all in one place. You'll be able to see there over the left, we in this instance have selected a Grover search as the algorithm. You're then operating at a slightly different level to what you might do if you were working in Qiskit or Chasm. You're working at a functional level. So we need to know what the mathematical expression is. We also need to have some definitions in order for that to be intelligible. We then also need to know which machine is on the back end. And there are many that you can select from. And as of that point, you can down tools after you've hit that synthesize button top right, and the software searches through that design space. And it's quite interesting in that you may often find yourself surprised by what is designed. A little bit like if you've ever seen the generative design that you have in mechanical engineering, where you tell the software what it is you want that bridge to do. How strong does it have to be? It has to connect point A to point B. You stand back, you come back. You would never have designed anything like that, but it'll be more efficient than you would have designed it yourself. It'll be lighter. It'll use fewer materials. It might be quicker to build. And it's very much the same thing that's going on under the hood here. Within the constraints and those particular functional needs that you have, you will get a circuit back. And as you can click through in this analysis screen, you'll find that it might not be the adder that you would have expected. And its location on which qubit it's using might not be the one that you would have intuitively have gone for. But it'll be more efficient, and importantly, it'll perhaps be much shallower as well. You can also select to constrain it for depth if you wish, which also in the utility area is a particularly important thing. So this is an issue where it's a much more intuitive programming approach. You're really thinking about the outcome that you want to get. You declare where you want to go, and you let the software navigate you to that destination. It's a little bit like this. You're sitting there looking at that whole problem space of how am I going to program for this computer? How am I going to get this program to work? And if you take it the more instructive way, you are very locally fixated. It's very, very closely defined. And there's some room for maneuver at that transpilation level, but you're not going to be surprised by the changes at the transpilation level as compared to this much more functional approach where the software understands where it is that you want to go and will take you there, perhaps in ways that you hadn't expected. And you can guide it in terms of what your preferences are. You'll be able to do so very, very quickly. You're talking about generating large, complex circuits in matters of seconds, or perhaps slightly longer for very, very large circuits. But you're generating something that you wouldn't have been able to think of yourself, no matter how expert. And certainly as those qubits keep piling on, it gets more and more complex. However, we're still in that utility era. And contrary to many situations, there are places where it's very good to be shallow. And this is one of the things that can really turbocharge people who are looking to make the very most of the computers that are coming online at the moment and next year. And we see all these investments over the last few months. We can expect greater and greater things in the months ahead, or the years ahead. Nevertheless, shallowness is going to be key. And if you're going to achieve that and think that you'll be able to achieve it using traditional approaches, life's going to get very tough. Here's an example of results that we've had on an ansatz, where using that generative design approach that based on the functional requirement that you have and that freedom to search that entire problem space, you can see the advantage that one gets in terms of the depth of the circuit, in terms of the CX gates, for example. And this is something that can dramatically change which kind of system you'd be able to work with. It might bring the results that you need much further forward. And the same thing goes for a host of other types of implementations. And so you're getting many things here. You're getting access to hardware that can actually do things sooner. You're generating your circuit much more quickly. And if you think back to that, the sort of the earlier slides, you're also going to be able to let people who don't have a PhD in quantum physics actually implement these types of circuits and then execute them all in one flow. So having lowered barriers for developers and taking this software as far as it can go, so the software is ready for whichever gate-based system out there needs to be programmed for. And that problem space will grow as the qubits grow, but since this engine is there ready and waiting for whichever needs that particular programmer might have. But obviously, what are you coding for? So there are so many machines coming online. There's so many new modalities. And one of the things that our enterprise customers often are in a bit of a quandary about is which is the one I should use? This one requires a commitment of X numbers of dollars, or this amount of training time for our team. What happens if it's not the right modality for us? What happens if it's not the right machine? And these are things that you perhaps want to de-risk. So one thing that we're doing at Classiq is allowing a smooth flow to a very broad range of backends, which partly via the cloud and partly directly. And on the other hand, we're seeing that the HPC community and the quantum community are really coming together. We were at the show in Denver not too long ago, demonstrating together with HPE ways in which one can integrate a quantum backend into a seamless flow with a traditional HPC interface, so that you really can bring all advanced computation under one roof. So what we're doing at the moment is we're working on those HPC integrations. You'll see at the top of the screen, we've got the IDE to be very welcoming for users of all kinds and help you with the heavy lifting. If you do prefer Python, there's an SDK. You can use that, and that's absolutely fine. But the IDE really lowers those barriers and makes it easier for folks who just want to get there as quickly as possible. Customizations, etc. Python is there to allow you to tweak whatever outputs you have. And you can take all of these different backends. It's a drop-down menu, it's a GUI, so whichever cloud provider you perhaps have an account with, you're welcome to do that, or directly indeed as well. And it also allows you to have scalability into the future. If your system that you use changes, you don't have to rewrite your code. You just resynthesize, change your constraints, and you're good to go. So this path to utility is built in. It comes with scalability built in as well. So in summary, this privileged position of being in software, we really do think of being in this sort of utility era, so it's utility and beyond, because we're ready to do the circuits for the systems that don't even exist yet. So if you want to explore and research those, that's also absolutely fine. So thank you very much. Please do come by the booth. We look forward to demonstrating it. Thank you.